right. Well, good morning, good afternoon, everyone, and welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Grabowski, and I'll be your host for today. We are into the 20s now in October. We've already had a ton of live classroom connections for you, a lot from this world of space exploration as we've connected with astronauts and scientists and engineers who are making exploration off our planet possible. But we always have a huge mixture of events, grabbing stuff from the worlds of science, exploration, conservation, and adventure. And today we get to do something that is one of my favorite things, and I think it's the classroom's favorite thing, is to go out in the field and see science in action. So today we are heading out to the Bering Sea to join a team of researchers as they steam towards their research site in newly forming sea ice of the Arctic Ocean on board a research icebreaker. So in this lesson, we're going to learn a little bit about landfast ice, why it's important. We'll learn a little bit about waves and storms and cold conditions in the Arctic. And we'll discover some of the tools that scientists are using to measure things like ice and waves, seafloor sediment, and we're going to get a chance to meet those scientists. So I'm going to reach backstage and see if I can grab those scientists right now. Hey everyone, how are we doing?
Morning.
Good morning.
All right. Well, awesome to see you. We're really excited to be connected. We've got classrooms joining us from Canada, from the US. We're going to get lots of Q&A time a little bit later. But first, we'd love to meet everybody and then learn a little bit about what you've been up to.
Yeah, so we're up here in the Bering Sea, as Joe said, on our way to the Arctic Ocean. Currently, we're just west of Alaska, going up through some wind and some waves. We're here for part of this project called Coastal Freeze. And you may have heard that the Arctic is changing. It's in general losing a lot of ice, but it still gets really cold every winter. Ice still freezes. And so we're going up during that period when ice is forming to understand how the changes that we're seeing in general in the Arctic are impacting that transition. And we're really interested in how the storms and mud and ice are interacting. So we're doing all of this research from our moving laboratory, the research vessel Sikuliaq, which will be our platform for the next few weeks to do the science. And we have an awesome team of scientists aboard to do that. We have about 15 scientists from our three different institutions that'll be part of this project over the next few weeks. So I'm Maddie Smith. I'm a scientist at the Woods Hole Oceanographic Institution, and I love studying ice and specifically sea ice, and so I'm really interested in that part of this project.
And I'm Emily Idem. I'm a marine geologist at Oregon State University, and I'm interested in the mud in the oceans that gets washed off the landscape and understanding where it goes and quantifying seafloor erosion.
And I'm Jim Thompson. I'm a researcher at the University of Washington in Seattle at the Applied Physics Lab. And I study the surface of the ocean where the atmosphere and the ocean interact and there are waves and where sea ice forms if it gets cold enough.
So we're going to tell you a little bit about the tools that we're using up here to make these measurements and do this science. So to start, I'm going to tell you about what we use to measure the ocean and understand whether it can freeze or not. So to help us understand if the ocean's going to freeze, it has to be really cold. And so we want to be able to measure both how the temperature of the ocean and how salty it is. And so the instrument that one of the main tools that we have in our toolbox to study that is called a CTD, and that can take a lot of different forms. So this here is a big version of a CTD. And so if you look down here, you can actually see the real sensors, the meat of it that makes those measurements that we're interested in are down here mounted on this frame. And so it has sensors that measure how much salt is in the water, how salty it is, and how cold it is, but also other things like how much oxygen is there, and some indicators of like how much plant life is in the water. And so that's one of the things that we're really interested in here. But the cool thing about this big platform that we use is that it also has these big canisters that you can see. And so when we put it in, we'll put them in cocked like that. And then when we put it down into the ocean, those will snap closed, and so we can capture water that we can then take samples of to measure lots of different things that might be in the water. Because on this project, we're really interested in looking at, we'll be mostly in really shallow water near the coastline. And so we're looking at we're going to use a smaller version that allows us to get into shallower water. And can do from a small vessel or more easily from this big platform. And so this is a smaller version of this instrument, the CTD, that allows us, that we can just deploy by hand and has a lot of those same sensors. So this version is obviously very big, and so we can't deploy it by hand. And so this big door that you can see behind actually opens, it swings all the way over there. And then this gets fully lifted over the side of the vessel out like 20 feet and goes down to the bottom of the ocean. We're out in over a mile. Yeah, we might measure down to a mile below the ocean to capture water and those different things that we're interested in.
Great. All right. Well, over here we have a very different type of sampling device. And Jim, if you want to start raising that up, we can do a quick demo. So this has a very fancy name. It's called a grab sampler. And we are using this to collect mud and sediments from the seafloor because we want to know what size material is down there, because that helps us quantify how fast the seafloor may erode under the influence of waves. So this device is kind of like a big spring-loaded trap, and it has a bucket that is retracted on a spring, and when it hits the seafloor, that spring is tripped, and we collect a sample very energetically, and we can slice through mud and gravel, and we can bring that back on board so that we can save it. We can look at the sizes, we can look at the chemistry. Sometimes we even bring back small organisms like sand dollars or sea anemones if they're on the seafloor. So we're going to do a quick demo of this for you, just so you get a sense of what happens when it hits the seafloor. And we're going to use some ice here as our fake seabed sediment. So imagine that this is mud. Okay, so now our device is armed and ready to go, and at this point we would normally be lowering it all the way down to the seafloor. We're going to go ahead and lower it into our bucket of fake mud. And you heard that sound, that was the bucket closing. And so now if we raise it up, we typically at this point bring it back on the ship and see what kind of sample we collected. All right, so in this case we caught some ice. That was our fake seafloor, but typically this is the point at which we would be pretty excited to see what we caught. It's always a little bit of a mystery what's down there on the seafloor, and we have to have creative ways like this to sample it. So that's the geology part.
Keep coming down. Okay, next up, I want to talk to you about how we measure waves, and we do that with wave buoys. So we got some wave buoys over here that we brought. And we actually have a few that are up there already in the Arctic Ocean that we put out before we went on this trip, and they're telling us data right now about what the waves are doing. And there's something really clear that's been happening in the Arctic lately. There's been less sea ice, and that means there have been more waves, bigger waves for a longer part of the season. So that's one of the key trends that we're tracking as the Arctic warms up, and there's less ice, there are more waves. More waves means a lot of different things. More waves means more mixing of the ocean. More waves means more coastal erosion, because that coastline was usually protected by the sea ice. But now with less sea ice, more waves, there's more activity at the coastlines. And it's just rougher up there in general when we take ships up there. So here's one of the wave buoys that we use. And these ones we make in our lab, so we do a bit of science and technology. We build these buoys here. So the yellow part's like a big life jacket for the buoy, keeps it floating. And then the rest of it has all the sensors on it. So there's some sensors down below, and those measure the turbulence, and they measure the currents in the ocean. They do that with a type of sonar, and that's something that sends sound out and can measure how fast the ocean's moving below. They measure the temperature and salinity. So part of that is very similar to what Maddie just showed you with the CTD. We're doing a similar measurement here, but only at the surface. We need the CTD to see down below. we use this to see what's happening at the surface. The other things we have are we have a weather station up here. It tells us how windy it is, what the air temperature is. And we even have a little camera on here, and the camera takes images to tell us what kind of sea ice the buoy is observing. So we'll get up there with a big ship and we'll put out a whole bunch of these, and they let us make measurements that are distributed. They're at many different places at the same time, instead of just only seeing what the ship sees. So the big advantage of these is being able to spread them all out and see what's happening really close to the coast and really far from the coast while the ship goes and does something else. So we'll put these out, and they'll call back to a server in Seattle using this antenna. They'll call every hour and they'll give us their data. And then when we're done, we'll hopefully recover them and we'll get even more data off there that's just stored on here. That's one version. We have a small version that we've recently developed that's pretty fun. We call it a micro Swift because that one's called a Swift. And these micro Swifts are small like this, and they're much cheaper and easier to build. They don't make all the same measurements, but they make a lot of the same measurements, and we're able to build a lot more of these. So we brought a bunch of these, and we'll also put these out. And in fact, some of these have already gone out ahead of time from an airplane. Because they're so small and they've got this cylinder shape, they can go out of a small hole in an airplane and they can be deployed ahead of time by some colleagues from NOAA who run an airplane survey up in this region. So they still float at the surface, they go up and down, and that helps us measure how big the waves are, what direction the waves are coming from. And then they have a little temperature gauge on the bottom, and they have a brand new sensor that we've done with Emily to help us understand how much the water is turbidity. That's the word that says how much sediment is in the water. Is it very brown, dirty water with a lot of sediment, or is it really clear? And we want to know that because we want to know as the ice is freezing, is there sediment getting into that ice? So this is a new measurement that we're able to do with that buoy. Okay, that's the wave buoys. I want to hand back off to Maddie.
Yeah, so now that we've covered the different tools that we're going to be using in this environment, I want to talk a little bit more about the science that we're going to be doing, so why we're making these measurements in the Arctic. So the area that we're going to is close to the coast. So ice forms throughout the Arctic Ocean in the fall and into the winter, but the ice that specifically forms along the coastline is a type of ice that we call landfast ice because it becomes attached to the coast and will become kind of solid there throughout the winter. It stays in place. It actually gets attached to the seafloor, so that kind of helps hold it there. And that's the reason we're focusing on that is because it's really important for protecting that coastline from the things that might, the storms that may happen throughout the fall and throughout the winter. And this ice forms in a slightly different way that's forming in the ocean. It's still forming as the water is cooling down and getting cold, but the process is going to look a little different, and so that's why we want to focus on understanding that in particular because of the value that it has for the coastline. And I don't know, Jim, do you want to talk a little bit more about why the waves, how the waves are impacting the coastline?
Well, the waves in the sea ice, we can go outside and have a look at the waves while we're talking about waves. How does that sound? Yeah? Okay. Let's follow me back out here and we'll look at some waves. This is good? Yeah. Okay, so we can see plenty of waves out here. And these waves out in open water, they're running free. They can do whatever they want. They can go for long, long ways. They can cross whole oceans. But the waves up in the sea ice, they don't get to go that far because of the ice itself. So we say that the ice damps the waves. It makes the waves smaller. So as freeze up occurs, we have two things constantly happening together. We're making ice and more ice is forming, and the waves are propagating into that ice, coming into the ice, and they're mixing up the ice, they're stirring up the ice, they're breaking up the ice, but the ice is also affecting the waves. So this is a classic feedback mechanism where the two things are affecting each other, and you have to study the two together to understand them well. If you studied one independently, you really wouldn't understand the whole system. So, and this is a key part of what we're doing, is measuring the waves and the ice formation at the same time, while also measuring how much sediment's in the water to understand how that's all happening together and how we make the ice that will become the winter ice pack and will eventually end up stuck at the coast. I want to hand back off to Emily as we can talk about the little boat we have behind us that we'll use and some of the other sediment sampling we'll use as the waves get in and are damped in the ice and there's sediment in the water.
Yeah, so one of the things we're really excited about, in addition to studying the waves and the sea ice, is studying the mud. Because when we get these big storm waves during the fall season as ice is forming, those waves stir up a lot of sediment. And you might wonder why we care about that. It's because when we stir up a lot of sediment off the seafloor, we can make really muddy ice. And we think that muddy ice is actually one of the ways that sediment gets removed away from Arctic systems, and it gets dumped into the really deep part of the ocean basin, and it just piles up there over thousands and millions of years. So we actually want to go study how much mud is getting into the ice. We can tell that it's muddy from satellite images in the spring, but we really need to get out there in small boats like this one and get out there with our sensors to try to collect some of that muddy ice and measure it directly. So this is a little landing craft. This can take us all the way to the shore. It's kind of a funny looking boat because it has that door on the front that we can lower if we need to get out on a beach somewhere. And so we will bundle up in some very thick parkas and some survival gear, and we'll take this out and go have a lot of fun going out for hours at a time to go sample near shore. And with that, I'll pass it back to Maddie.
Yes. Oh, I don't need that one. I already have one.
Oh, yeah.
Yeah, so I'll just point out a few more things of the tools that we use back here on the deck of the ship. So this is where we really go out and do our science from. So sometimes it'll be from that small boat, but there's also a lot that we'll do from this platform here. So right here is a crane that we'll use to lift out some of the instrumentation into the water. So that's one way that we can deploy the CTD and other instruments. And then that back there that John's pointing at right now is this that we're looking at is the A-frame. And so that's a bigger, can lift a lot of, can hold a lot of load, a lot of weight. And so we'll use that also to lift up instruments that we've deployed on the seafloor that are out there measuring right now. So that can lift them up and bring them back onto the ship to take them home. Yeah, and so back up on the, looking towards the bow of the ship, we can see some of the different places that we can control instrumentation from. So there's this room here is what allows us to lift out the CTD out into the water. There's also a lot of other instruments on the ship itself. So up on the mast at the very top are instruments that are measuring things in the atmosphere. So we can see how windy it is, which is really important. How windy it is, how cold it is, that helps us understand how much ice we're likely to form, which is something we're obviously really interested in. Yeah, and lots of other sensors measuring the atmosphere and the upper part of the ocean that help contribute to that story. So let's go back inside where it's a little warmer. Yes, the Arctic is changing really fast, and these measurements that we're making to understand how waves and ice and mud are interacting are hopefully going to be really helpful in better understanding the changes and how that matters for the Arctic ecosystems and communities that live along the coastline. Yeah, so are we ready to, I think we're ready to take some questions if that works for you.
All right, that absolutely works for us. Maddie, Emily, and Jim, thank you so much for that great tour, that great exploration. Oh my gosh, that view out over the water is absolutely incredible. Really beautiful, the place you are right now. But let's get into some of that Q&A action. If you are tuning in via YouTube, don't be shy. Use the chat sidebar. Send us in some questions. I've got some camera classrooms backstage, so we're going to visit those classrooms, and we're going to get some questions from them. So maybe I'll start off. Let's see. Go over to my list. Okay, let's start off in Michigan. We have some 6th graders hanging out with us in Michigan. I'm going to bring them into the stream. Hey, DeWitt Middle School, how we doing?
All right, the camera's right here, Nolan. Nope, there you are. You're on camera. All right, ask your question. That's right.
How do you make sure that the wind doesn't ruin, how do you keep protection when all of the wind is coming?
So
Like
I got some of that. You're worried about the wind breaking the connection with what?
with their sound or the internet or
Yeah, with
their data.
Okay. So they're wondering how the wind can impact your data collection and the equipment.
All right, you can have a seat. You got one too.
I'll take that one. So yeah, it is definitely very windy in the Arctic all the time, and that definitely affects our instruments and our work. And we do lose internet pretty regularly, and all of a sudden we don't have a signal anymore, and we have to be ready to work without that signal. We make plans ahead of time and make sure that we're ready to not have connection to the outside world. And we tie everything down, everything. Anywhere you walk around the ship, everything has a strap around it and it's tightly tied down, both outside and inside the ship, because the wind is constantly pushing things around and the ship's constantly rolling. So we think about the wind all day, every day, and we just assume it's always going to be stormy, and then we're never disappointed.
All right. Question here from YouTube, and then I'll check back in with our Michigan crew. How long will this expedition be going for in total?
We're going to be up here about 3 weeks. We have about 2 weeks that we're really going to be focused on site, making a lot of observations. Right now, as we mentioned in the beginning, we're kind of in the transit, so we're just passing through from where we started to where we're hoping to make those observations. But that's part of the total time of this trip. That's a little under a month. Yeah, and in early November we'll be doing another one of these live streams. Hopefully after we've collected a lot of data, and so we'll be able to check back in on how it went, and hopefully have some cool things, some early results to share.
All right. Obviously, we're very much looking forward to that. Let's see if we can grab one more from our Michigan crew before we visit another classroom. All right. Okay. So I don't know if you caught that. They're wondering about the materials that you use to create the devices. I think he's talking about, are you talking about the Swift buoys? Yeah.
Yeah, so the question was about materials. The salt water is very corrosive, so we worry about materials a lot. The salt water, I say that it eats things, and it loves to eat metal. So we do not use regular steel. We use aluminum, and then we use a fancy coating to anodize that aluminum. So this part right here, that's anodized aluminum. It's got this really tough coating on the outside of it. And then this is just plain foam. And then all of the fasteners, the bolts, nuts and bolts, those are all stainless steel. And then we even have these little plastic washers that isolate one metal from the other metal. Because if you put the two metals together in salt water, they will eventually have a big fight, and everybody loses in that fight. So this is a great example of a lot of engineering really being combined with our science. So we are scientists, but we have a lot of engineers who are on board here helping us do this and helping us do the design work on these things and making sure that the materials are the right materials that can survive in the ocean.
Okay, I'm going to grab one more question from YouTube before I bring a camera another camera class from Canada in here. But this one on YouTube is wondering how big the crew is on board right now.
Ooh, that's a good question.
24.
So we have about 24 crew on board, and we have about 16 science party members. So it's a really nice sized group right now. It's like our little mini town on board the ship.
Yeah, and the crew serve a wide variety of different roles on the ship. There's, from the captain, who's the one driving the ship, to, we have really good food on board. There's, 3 people who are working in the mess, so basically making sure we're well fed, which is awesome. And then a bunch of engineers working down in the engine room. So there's a really wide range of skill sets that are part of the crew that are help support our science beyond the scientists in our group here.
All right, let's grab a camera classroom here. Although I think they're joining via audio. We have Miss Collins' crew joining us in Fergus, Ontario. They're grade 5-6s. Let's get them in here. Hey, 5-6s, how are we doing today?
We are great, thank you.
All right.
So we have 3 questions, but one right at the moment.
Perfect.
Yep.
You know that thing that you used for the ice?
To grab the ice?
Yeah.
Okay.
Is that sharp?
Sharp.
Oh, that's a really great question. So the sampling device that we use, we have this scoop that fits inside of it. And the edge of this is a little bit sharp. It's sharp relative to the seabed. It's not so sharp that I can't touch it with my hands, but it can slice through pretty thick mud or sand. Sometimes we can even scoop up gravel with this. And the real power of this is those springs apply a lot of force to that sampling container so we can get a really good sample. Great question.
Okay. Let's grab another one of those questions, Ms. Collins Crew.
All right.
If the camera is on the buoy, how does it take pictures from all the way up in the sky?
Oh, okay. That question's about the camera on the buoy. It's on the buoy has a little mast, and it's just on that little mast, so it's not taking it up from high. So it is kind of a funny little field of view. That what it sees is as if you're right down in the water, almost as if you were swimming in the water. That's the view that it sees. So it only takes a picture of the ice that's just right in front of it, maybe only a few meters by a few meters, but it's enough to tell us that whether it's in ice or not in ice, or what type of ice it's in. And this is a fun one. On this trip, we're really hoping to see a particular type of ice. I hope you're ready for some jargon. It's a very technical term. It's called pancake ice because it's shaped like pancakes. And these little circles form when ice is being made, ice is forming, and there are waves around, and the waves make the ice all bump together, and they make these circular shapes that we literally call pancake ice. And that's our technical term for it, pancake ice. So we're hoping when we put these buoys out, we'll get some images of pancake ice from the buoys.
All right, great timing. I had a little video clip that John sent me in advance so students can see right now what the pancake ice looks like, and I think it lives up to its name pretty well. That's pretty cool looking ice. All right, Ms. Collins Crew, we'll check in with you in a little bit and see if we can grab another question or two before we wrap up today, but I'm gonna go back to YouTube. You've sold life out there on the ship pretty well, because I've got a question here wondering if you ever take volunteers to help collect data.
Do we? Yeah, occasionally there's opportunities. I mean, there, like for some projects, getting on a ship like this is a really long process. We spend a really long time planning and working on the plans for what we're going to be here, but especially there's different programs that help bring educators out onto vessels, as well as sometimes undergrads or students from universities around the country. So there's opportunities kind of to volunteer through these different types of platforms. There's a STEM program called STEM Seas, which brings out students. And then what's the polar? There's one for teachers that's called Polar STEAM that brings out educators from around the country as well. So yeah, there's kinds of ways to get involved like that. And in general, in oceanography and polar science, there's other opportunities for kind of like citizen science for people to participate remotely in contributing to the science that we're doing. So great question.
All right, very cool. I've got a class in Toronto wondering about the ice. How thick of ice can the ship handle?
So there are different classes of icebreakers. We call them different polar classes. And this vessel is actually not a true icebreaker. It has a super thick reinforced hull, or that's the shell of the ship that allows it to break ice. It doesn't quite have enough engine power to be classified as a true icebreaker. But despite that, it does very well at breaking ice, and it can break a lot of ice. And I want to say it can break up to at least a meter of ice.
Rated for a meter, but I think it can do more.
Sometimes it does more. And there are places in the ocean where the ice runs into itself, and there are these collision zones where you get a big pile of ice that's even bigger than a meter. We call those pressure ridges. And this ship can go through some of those. And if the pressure ridge is too thick, you just feel the ship stop, and then they back up and they find a different way to go through the ice. So they're very adaptable.
Okay, I've got some fourth graders in Florida who would very much like to know what the food is like on board.
You want to so pointing at Jim.
Food is quite good on board. It's great, and it keeps the morale up. There are 3 people working the galley who make the food every day, and they're on a rotation. And they take great care of us. They have a big walk-in freezer and refrigerator. They keep all the food fresh, and they really keep us going. We will, while we're out here, be working around the clock, and there'll be a lot of us working overnight. I have an overnight shift through the midnight, and so we'll also be in there. We're heating up leftovers and things from the meals the day before, and they make sure that there's always a lot of that available for us, and make sure that we're really, taking care of ourselves so that we can do a month out here. I think it's great. So I think we've sold that pretty well. The food is good and it's fun being out here on the ship. I will say though, the ship is always rocking and rolling and moving. So some people do not sleep well out here. Some people get a bit seasick, and it's not all roses. But the food part's really good.
Yeah.
Okay, let's get another question here from YouTube. This is from Caesar. Caesar's joining us all the way from Nicaragua, and Caesar would like to know: are the buoys anchored? And if not, how do you find them to pick them back up?
Do you want to do that, or you want me to do it?
Here.
Okay. So it's a great question because some of both. So there's basically 9 instruments total that we put out earlier this summer in September that are anchored, that are on kind of, basically what we call moorings. And so some of them have this buoy at the surface, but it has a line and a chain down to an anchor on the bottom that'll hold it there. And then we're going to go and pick them up before while we're up there in the next few weeks. But there's also the one that Jim showed you that we're bringing with us now. That is going to drift. So we'll put it out into the ocean, and it'll move around. It will move with the wind and the waves and the currents and kind of a mix of all the things that are moving around the ocean. That buoy will follow it. And so we will have to go chase them down to pick them up. But we have a lot of different ways that we can know where that is. I don't know if we want to look at it again. So it has 3 different ways of tracking. So it does send through the antenna that's sending the data, also sends the location. So it's telling us where it is. But it usually only does that about every hour. But it also has on there, this is a redundant tracker that sends through a different method where it is. And so that provides us some backup. And then there's another tracker that we can strap on before it goes out. So we have a bunch of different ways to track them down, because especially once it gets really cold and there starts to get ice, it may get a little harder for it to communicate. So it's nice to have some kind of backups on how to find them. Also, when it's dark, there's this little light here in this, it's kind of cased in there. That when it's dark in the Arctic, that light that's flashing is really bright. And so that'll also help us see them out on the horizon.
Okay, I'm gonna grab Miss Collins' class from backstage again and see if they have another question for us. Miss Collins, if you're ready, go ahead and unmute the microphone. There we go.
Okay.
What do the sleeping quarters look like?
So there are a couple decks on the ship that are sort of set up like hotels. There are a series of bunk rooms, and there's 2 bunk beds per room. So we get to sleep in bunk beds. And then 2 rooms share a bathroom, so 4 people share a bathroom. And the rooms are pretty nice. It's nice to just have 2 people in a room. They're pretty cozy. We definitely have to tie things down in there. There's a desk with a chair, and on really rough nights, the chair might go flying across the room if you don't tie it down. So we tie everything down. And then, what we call the galley or the mess, that's where we eat. That's right next door across the hallway. So one of the great things about being at sea is it doesn't take you any time to get to where you need to be. You can roll out of bed and be having breakfast 2 minutes later, and 5 minutes later be downstairs ready to go do some science.
All right. Miss Collins crew, I'll check and see if there's one more there.
Nope, that was everything. Thanks.
All right. Thanks, Fergus. Okay, so a few more here online. This is Maritime High School in Des Moines, Washington. They'd like to know what opportunities you would recommend for high school students interested in this field, marine sciences.
Seattle local?
Well, I'm from Seattle, so hi guys, and I can have a few things to say about that. First of all, if you're in a science classroom right now, do well in science and really spend time with your science and math, do your homework, and take that seriously, and that'll launch you in the right direction. In the Seattle area, there actually is a new high school that's a focused school on maritime careers, which is a really cool thing that you could look into. And that might send you on a path to be one of the crew on a ship like this, or to be a scientist on a ship like this. And either way, you would know more about working out and on the ocean. Other things you can get involved with there's some more technology-focused things, like there are underwater robotics that you can get involved with as a high school student, and you can go to these competitions and try to build the best ROV that makes it across a swimming pool the fastest or picks up an object from the bottom. And these are really applied to the kind of science we do out here. You know, we are doing more and more of our science with robotics, with autonomous platforms that can go reach places we can't get to safely with the ship or with people. That's where the robotics come in. So that's a big part of our work. So you can start to build your skill set in that direction. And you can just get out, and every chance you have to talk to people and learn a little bit more, you know, take advantage of all those opportunities. You never know which one's going to be the one that really launches you in the direction you want to go.
All right. Some follow-up from our fourth graders in Florida, wondering if it took anyone some time to find their sea legs on this trip.
Sure did.
Definitely. I've been going to sea for about 15 years now, and on this cruise, it took me about 2 days to get there. This ship, because it's an icebreaker, it has a very flat hull. There's different styles of icebreakers. Some have a sharp hull that cuts through the ice. Some have a flat hull that's meant to ride up and crush the ice. And this ship has a very flat hull. It is not built for waves. It rides the waves very poorly, and it bobs around a lot, and there's a lot of motion. So it often takes, even those of us who've been doing this a while, a couple days to get our sea legs.
Okay, I've got a two-parter here from a group on YouTube wondering, so this is actually Rowan is asking, how long is the ship? And then the second part to the question is, do the buoys ever get stuck in the ice?
It's a question for Jim.
The ship's about 250 feet long, which is pretty typical for a big ocean-going research vessel. And then the buoys do get stuck in the ice. They definitely get stuck in the ice. And when that happens, we do a couple of different things. We can bring the boat in, the icebreaker in, and we can do this clever thing where you turn the boat around. Remember that the boat can break ice, right? So the boat can sort of turn around, and then we can take the propellers at the back of the boat and aim them at the buoy, and then, you know, hit the throttle, and it'll chew up a bunch of ice, and it'll sort of turn it all into a big blender. And that's a little dangerous because the buoy might get caught in the blender, but the ship's crew have figured out how to do this pretty well. So we can break up a bunch of the ice around the buoy, or we can try to just creep up on the buoy and get a pole or a grappling hook on the buoy and try to pull it out of the ice. And this is actually one of the things we hope happens. That's the best case, is to get that data all the way through from open water when the ocean's not frozen, through some of this pancake ice formation and the waves and the ice and everything happening together, all the way through until fully frozen. And then at that point we can see, is there sediment in the ice? How long did that take? How windy was it? How cold was the atmosphere? How was everything working together in the whole system to get to that end point? And hopefully we get the buoy back, but the buoy has all these antennas on it so that we can get that data even in the case that we lose the buoy. We still got the data, because that's what we're really here for, is to get the data and then analyze the data and understand how that's all working.
Okay, I've got one last question here from some high schoolers in British Columbia, and they're curious, is the data you're collecting on this trip, is it baseline data, or do you have data from before that you're going to be able to compare it to?
That's a good question. Yeah, so all of us have actually been working up in this area in general for a while, you know, at least 10 years. And so we have some data that has helped us kind of get a first look and start to understand the types of things that we're interested in, from moorings that have been out through over the course of a year, or observations that we've made in the fall. So that data that we've collected on prior expeditions and fieldwork has kind of laid the groundwork for us to really have this more processed set of measurements that we're making on this expedition. So yeah, hopefully this will really allow us to answer some of these questions, but we'll also continue to be, I mean, things are changing, so anything we collect now is still a baseline, hopefully, for future observations to compare to, because of the really complete set of observations that we'll make.
All right. And final question here, as we prepare for hopefully connecting in a couple weeks from now, you know, expeditions are notorious for not always going as planned. You have to be flexible and ready to try the thing. So, you know, in a perfect world, what are the next 2 weeks going to look like?
Yeah. Well, we've already had some changes from plan, so we're adapting and we'll continue to adapt. But the next couple weeks, hopefully, you know, by the end of this week, we'll hopefully be on site where we're hoping to focus over the next couple weeks. And so as we mentioned that there's some instruments that are out there that have been measuring, kind of working hard over the last month and a half or so. It'll be almost 2 months by the time we get there. So one of our first things to do will be to pick those up and see what's on them and then get them ready to go back out. And then we'll be doing Jim's mentioned that we're working around the clock. We'll be going out in the small boat, like that boat we saw earlier, and making lots of observations. And hopefully by the time we leave and we get back to you in early November, that whole area will have frozen up. We'll have seen some storms come through and there'll be a lot of ice. So yeah, in our ideal world, we'll have seen that all play out, have brought all our instruments back and be heading back, but we'll let you know how that changes.
All right. Well, wishing you best of luck and safe travels out there collecting that great science data out in the Arctic. I want to start off with a huge shout out to our classrooms who joined us backstage. Thank you for those great questions. A shout out to the classrooms who joined us live via YouTube and sent in great questions. And of course, a shout out to those who will tune into the recording later. Thanks for joining in to learn more about this really cool expedition. Maddie, Emily, and Jim, thank you so much for being available to hang out with us today. Give us a little look at the ship and the science that's happening. And of course, a shout out to John as well behind the camera for helping organize this and being so steady on the camera today.
It's a challenge. Thank you. Really great to be here with you all. Thanks for your time.
All right. Thanks, everyone. Hopefully we'll see you in a couple weeks.
Awesome.
Good.